All right, for 8182, we're doing arc length and surface area. So just like we did with integration, where we found the area of a little rectangle and we added up all these rectangular partitions, and then we brought in the integration by looking at the sum of those areas as the partitions became infinitely small or as we got infinitely many partitions. We brought in our integral to give us total area under a curve. So we're going to look at little partitions of length, right, of distance along a curve, and as we get infinitely many of them again, we can use an integral to find the entire length of a curve. But we can write out some stuff to hopefully make it make some sense. And starting with just little labels down here, if we call one x sub I minus 1, the next x value is just an x sub I. And we know y sub I minus y sub I minus 1 over x sub I minus x sub I minus 1. It would be the same thing as saying delta y sub I over delta x sub I. And that's what we call the slope, right, of that little segment, or our average rate of change. So we'll bring those in a sec, but our distance formula, just for a nice straight line distance, d equals square root of the quantities x2 minus x1 squared plus quantity y2 minus y1 squared. So we can find the distance over every little segment or every little interval, and we can write that as a d sub I equals square root of x sub I minus x sub I minus 1 squared plus quantity y sub I minus y sub I minus 1 squared. And then knowing again that that delta y delta x is just a change in y or change in x, we can simplify this formula with a delta x sub I squared plus delta y sub I squared. Right, so for each little interval, change in x, change in y. And then we get something from our mean value theorem that brings in the calc and brings in a nice derivative so we can get rid of those average rates of change by the mean value theorem. We get some value c sub I, which is in the interval x sub I minus 1 to x sub I, such that f prime of c sub I is equal to delta y sub I over delta x sub I. Right, our mean value theorem in Calc 1 for derivatives said if we had that nice continuous function on the interval, there was some value c in there where the instantaneous rate of change was equal to the average rate of change. And so we'll use that result to get rid of some of these average rates of change to bring in our derivative. And so we can solve for this delta y sub I and say it's equal to f prime of c sub I times delta x sub I, just by multiplying over. And then we can sub it in. So with that, we get our distance here is equal to square root of delta x sub I squared plus, when we square, we've got f prime of c sub I squared times delta x sub I squared. And since both factors have that, or both terms have the factor x delta x sub I squared, we can pull it out of the square root. So we get here, our distance is now a 1 plus f prime of c sub I squared times delta x sub I. All right, and again, for the integral or for the sum of all these segments to give us the total length of the curve, we just want a summation. So we can say our summation here now from I equals 1 to n of our curves, or all of our little pieces, the 1 plus f prime of some c sub I in there, quantity squared, times the delta x sub I, will give us the total length of the curve. All right, and then all we want to do is take the limit as n approaches infinity to add up infinitely many partitions, or look at what happens as we approximate this length as best as possible, and work from just adding up a bunch of little segments to integrating over the curve to get our total length. So we've got the limit as n approaches infinity, sum from I equals 1 to n of square root of 1 plus f prime of c sub I squared delta x sub I. And that's going to give us s we usually use for arc length. S equals our integral from a to b, right, to take us over that whole interval we're finding the length of. square root 1 plus f prime of x squared, and then the delta xi becomes our dx, right? Our little increments with respect to x. So this is the formula we're working with. We can also use, if we're in terms of y, right? If that's easier to work with, they'll use c and d instead of a and b, but f of a, f of b. Square root of 1 plus f prime of y squared dy. So either one can be used. There's still just different ways to express the same curve, right? Like a line, we can solve for x, we could solve for y, but they both represent the same line. So either one will work. Whichever one's easier to work with, you'll use for the problem. But let's try some problems. All right, so for one here, we're finding the arc length from x sub 1, y sub 1 to x sub 2, y sub 2 on the graph of f of x equals mx plus b. So kind of just reconciling that this formula does give us straight line distance, because you could obviously just use the distance formula for that. But if we look at the process here, our f prime of x is just m, right? It's the slope. And the slope of that line is just y sub 2 minus y sub 1 over x sub 2 minus x sub 1. So if we fill this into our integral here, we'd get that our arc length s is equal to our integral from x sub 1 to x sub 2, square root of 1 plus the slope m, f prime of x, so y sub 2 minus y sub 1 over x sub 2 minus x sub 1 squared dx. And then we can go through and simplify and work things out. So our integral from x sub 1 to x sub 2, underneath there, we could get, if we get a common denominator, we'd have x sub 2 minus x sub 1 quantity squared plus a y sub 2 minus y sub 1 quantity squared all over x sub 2 minus x sub 1 quantity squared dx. And what might be hard to see or think about, but again, you're not going to do tons of problems like this, so hopefully easier for other ones. This whole expression is a constant, right? X sub 1, y sub 1, x sub 2, y sub 2 are all just numbers, right? Those are 2 points along this curve. So this whole thing is just a constant, which means when we integrate, we're going to get this whole big square root. And I can maybe take that denominator out, make it a little easier on myself to write. But our numerator would be stuck with the x sub 2 minus x sub 1 quantity squared plus the y sub 2 minus y sub 1 quantity squared all over, right? Square root of that squared would just give us an x sub 2 minus x sub 1 and then an x here, right? So this is a constant, so the constant times x would be our antiderivative, and we're just evaluating from x sub 1 to x sub 2. And if without doing too much more writing, so we can get into more of the problems you actually do, we can rewrite the numerator as is, right? And then leave our denominator, x sub 2 minus x sub 1. And maybe just think about it this way. We pulled this whole constant out, right? And then we're evaluating x from x sub 1 to x sub 2. So using our fundamental theorem of calculus, that would give us an x sub 2 minus x sub 1, which cancels out with the one we've got in the denominator. And we can see that our formula for arc length, when we find the length of a nice straight line, still gives us our normal straight line distance formula, the square root of x sub 2 minus x sub 1 quantity squared plus y sub 2 minus y sub 1 quantity squared. So basically it just agrees with what we already knew. All right, so there's the back and forth of it, and we want to try some actual problems. All right, for 2 then, we're finding the arc length of the graph of y equals x cubed over 6 plus 1 over 2x on the interval 1/2 to 2. So we want to start by finding the derivative, y prime or f prime of x. 3x squared over 6 would be x squared over 2. And then that x to the negative first would give us a minus 1/2 x to the minus second, or 1 over 2x squared. And then we can plug into our arc length formula. We've got an s equals our integral from 1/2 to 2, square root of 1 plus that derivative we just got squared, so x squared over 2 minus 1 over 2x squared quantity squared dx. And then we'll just run through doing a lot of algebra until we get something we can integrate. So integral from 1/2 to 2. If we expand that binomial under there, we get a 1 plus x to the 4th over 4. If we multiply those two together, we get a 1/4. Right, the x squared and x squared will divide out, and then times 2 gives us our little shortcut there, so we get just a minus 1/2. And then the second term squared would give us a plus 1 over 4x to the 4th. All right, dx is still there. Our only like terms, and you'll see this happens quite a bit for these problems, we're going to change that minus 1/2 in the middle to a positive 1/2, right? Because we've just got 1 minus 1/2. So our integral becomes integral still from 1/2 to 2, but underneath we get an x to the 4th over 4 plus 1/2 plus 1 over 4x to the 4th. All right, and again, something you might have to get used to. You might be able to simplify by taking out the 1/4, and then you can think about it more easily. But this is still a perfect square trinomial. All we did again was change that middle term from a minus 1/2 to a positive 1/2. So instead of x squared over 2 minus 1 over 2x squared, this is going to be a perfect square trinomial, which would factor into the form. So our integral 1/2 to 2 still there. And underneath this square root, we're going to have an x squared over 2 plus 1 over 2x squared. All right, and you can check it, but again, all we did was change that middle term from a negative to a positive. It still has that same value, 1/2. So would be twice the square roots of the first and third terms multiplied together. So like x squared over 2 times 1 over 2x squared times 2 would still give us this 1/2. So it is a perfect square trinomial. We can talk about it more, but when you practice, you'll see it. They'll start to pop out a lot. You'll see that same kind of format come. And then once we've got the square root of something squared, we can rewrite our integral as integral from 1/2 to 2 of just x squared over 2 plus 1 over 2x squared dx. And we could maybe factor out the 1/2, but I don't know if I need to write another step, so let's just do it. We'd have x cubed over 6. And then when we integrate over there, we get a minus 1 over 2x. And we're evaluating that from 1/2 to 2. When we evaluate, we get an 8 over 6, or 4/3, but we'll see if we need it, minus a 1/4, minus whole quantity here, plugging in the 1/2, we get a 1/8 over 6, or 1/48, minus 1. All right, and if we put all those together, we end up with a, 16 minus 3, or 13/12. And then that's going to be a plus 47 over 48. So 52 plus 47, right? If we multiply by 4 here, 4 and 4 to get the 48, gives us a 99 over 48, 33 over 16. So hey, we'll go there. And it's slightly more than 2. You can get an approximate, but we'll follow that process for a lot of them where we end up squaring some binomial, simplifying, and then still having this perfect square trinomial that'll help us get rid of things. For 3, we're finding the arc length of the graph of quantity y minus 1 cubed equals x squared on the interval 0 to 8. If we do take a cube root and try and solve for y, that x to the 2/3, its derivative is not defined at 0. Right, we end up with the x to the negative 1/3, or the x in the denominator. So we'll solve for x here and do this one in terms of y, just so you can see both as well. But all we need to do is take a square root to solve for x. So x would be equal to y minus 1 to the 3/2. And then our x prime, our derivative, would be a 3/2 quantity y minus 1 to the 1/2. And chain rule would just bring in a 1 from the coefficient of the y there. So nothing else to write. We do also want to make sure our bounds are in terms of y if we're doing everything with respect to y. 0 to 8 is an interval for x. So if x is 0, we get that y minus 1 cubed is equal to 0. Cube root still 0, so y minus 1 equals 0, or y equals 1. And if x is 8, we get the y minus 1 cubed is equal to 64. Cube root of 64 is 4. And then adding the 1, y is 5. So for our arc length s, we're going to integrate from 1 to 5. Underneath our square root, we'll have a 1 plus that square root over there, the 3/2 times the quantity y minus 1 to the 1/2, all squared, and then dy. And we can work down, simplify algebraically. If we do square that whole mess, we get a 9/4 times the quantity y minus 1. And then just continue to simplify, integral from 1 to 5 of 1 plus 9/4 y minus 9/4. The 1 minus 9/4 will give us a negative 5/4 underneath. So integral from 1 to 5, square root of 9/4 y minus 5/4. We can factor out the 1/4. Taking it out of the square root would put a 1/2 out front. So 1/2 the integral from 1 to 5 of square root 9y minus 5 dy. And again, not something you have to write out the u sub for, but I'll do the little u sub so we see it. But u equals 9y minus 5. Du then equals 9 dy, or du over 9 equals dy for our substitution. And then our bounds as well. If y equals 1, u would equal 4. If y equals 5, u would equal 45 minus 5, or 40. And then we can sub back in. So we get our integral, 1/2 times the 1/9 that comes in from du over 9. Integral from 4 to 40 of just u to the 1/2 du. And let's just finish over here. The 1/2 1/9 will give us a 1/18. And then we're also going to multiply that by the 2/3 that comes in from our integration, right? We'd end up with a u to the 3/2 times that 2/3, evaluated from 4 to 40. And so we get a 1 over 27 times our quantity here, 40 to the 3/2 minus 4 to the 3/2. That one's just 8. And then I've got an approximate here because, I don't know, we don't like to leave it like that. So 9.073. I'll tell you where to round if we get problems on the test, or hopefully they'll tell you in the homework. But that's it. Nice process. Little u sub. Again, you don't have to do it. You know a 9 would have come in from chain rule, so dividing by 9 would have done the same thing. And you could just integrate 2/3 that thing to the 3/2 like you've done for a lot of square roots in the past. But u sub's there if you need it. All right, for 4, we're finding the arc length of the graph of f of x equals natural log of cosine x from 0 to pi over 4. So we're going to look at f prime. Natural log of cosine x would be a 1 over cosine x times derivative of cosine x, which is a minus sine x. So minus sine x over cosine x would give us a minus tan x. And when we sub into our arc length formula, then we're integrating from 0 to pi over 4. We've got a square root of 1 plus, it's a minus tan x quantity squared, so just a tan x squared. So our integral from 0 to pi over 4, underneath our square root, 1 plus tan squared x, and let me get all my dx's. All right, and 1 plus tan squared, we've done a lot of the trig sub and trig integrals now, so we know that's equal to secant squared x. So the square root of secant squared x would just give us integral from 0 to pi over 4 of secant x. And I think I've written that one out enough. If you need to see it again, multiply by secant x plus tangent x, numerator and denominator. That becomes your u. But our integration would give us natural log of secant x plus tangent x then, evaluated from 0 to pi over 4. So we get a natural log of secant pi over 4. Cosine of pi over 4 would be root 2 over 2, so secant of pi over 4 is just root 2. Tangent of pi over 4 is 1, so we get natural log of root 2 plus 1 minus natural log of, if we sub in 0, Cosine of 0 is 1. Secant's going to be there as well, right? That's where it'll bounce off each other at that max. So natural log of 1. And tangent of 0 is 0. So just natural log of 1 there. That whole natural log of 1, right, is 0. So we end up just with the natural log of root 2 plus 1. Do I have an approximate? Somewhere, maybe. Yeah, 0.88. And then one more arc length. We're finding the length of the arc of the parabola, y squared equals x, from 0, 0 to 1, 1. It's already solved for y, so we might as well do another one in terms of y. So if we've got x equals y squared, right? X prime is just going to be 2y. And then for the y's, we'd be going from 0 to 1 as well, but just to highlight the y's. So our arc length s is equal to square root, or not square root, well, we'll have it, but in a sec, our integral from 0 to 1 of the square root of 1 plus 2y quantity squared dy, which is going to give us our integral from 0 to 1 of a 1 plus 4y squared dy. All right, and that takes us back to trig sub. We don't have anything really nice there, but y is going to be equal to a 1/2 tan theta. And so y squared would be 1/4 tan squared theta. And for our bounds, if we're putting everything in terms of theta, if y equals 0, right, tangent of 0 is just 0, so tan inverse of 0, also 0, so theta is 0. And then if y equals 1, we'd have multiplying the 2 over, so 2 equals tan theta, or theta equals tan inverse of 2. And last thing we'd need would be dy. So dy is going to be a 1/2 secant squared theta d theta. All right, so filling in all our pieces there, we get our integral from 0 to tan inverse 2. Underneath our square root, we've got a 1 plus 4 times 1/4 tan squared theta. And then outside, we'd have the 1/2 secant squared theta d theta. All right, so I think I plugged everything in, right? And then underneath the radical, we will simplify. Right, that'd be the one that's just secant theta, but we can write out another step. Maybe I got room. 1 plus tan squared theta times, we can bring that 1/2 out front, times a secant squared theta d theta. Gives us 1/2 integral from 0 to tan inverse 2. Underneath now we'd have secant squared, so just secant times secant squared, which would give us a secant cubed theta d theta. All right, now how much room I got? There's some room down here. I'll do some scratch at the bottom. We've done this before, but if you don't remember it, haven't seen it in a while, I think I kept this one in the notes, so we do the secant cubed again because it seems to come up a lot. All right, and we'll do the integration by parts for the secant cube down here. So let's just do integral secant cube theta d theta. For that, the u is going to be our secant theta, and the one we know the antiderivative of, our dv, is going to be the rest, so secant squared theta d theta. Du then is going to be secant theta tangent theta. And v, when we integrate, is going to be just a tan theta. All right, we can throw the d theta there. So our integral here is equal to u times v, so secant theta tan theta minus integral v du, so secant theta tan squared theta d theta. And then we just want to expand that second piece, so secant theta tangent theta minus integral secant theta times secant squared theta minus 1 d theta. And that's equal to secant theta tangent theta minus integral secant cubed theta d theta plus our integral of secant theta d theta. All right, and so what we want to do, similar to those kind of cyclical ones with the transcendental function sine, cosine e to the x, we did it once before, but we'll add this secant cube back over to the other side. And so here, let's call this I, just so maybe I can fit everything. So we end up with a 2I equals secant theta tangent theta plus integral secant theta. And integral of secant theta we just did up above, or reminded you of what it was up above, but we'll divide by the 2 to get a 1/2 here out front. And the secant theta tangent theta stays, plus our natural log of secant theta plus tan theta. All right, so that was our secant cubed with integration by parts we did back in 7.1, but that was maybe the last test, so you're seeing it again here. And then we can bring that stuff up so we can maybe finish. But we get a 1/2 here, and then we're going to bring in another 1/2 from, right, just subbing in this whole value down here, right? This is secant cube theta d theta, or integral of secant cube theta d theta. So we get a 1/2 secant theta tan theta plus natural log secant theta plus tan theta, all evaluated from 0 to tan inverse of 2. And so that leaves us with a 1/4 times a whole bunch of stuff. So secant theta of tan inverse 2, so secant of tan inverse 2, we can just draw out a triangle over here. We'd have theta equals tan inverse 2, so tangent theta equals 2. Back to some trig, so 2 over 1, which makes hypotenuse the square root of 5, right? 1 squared plus 2 squared. And then secant then would be that hypotenuse over adjacent, so we get a root 5. Tangent of theta would just be 2, so root 5 times 2, plus natural log of root 5 plus 2, and then minus, if we sub in the 0, tangent of 0 is 0, so that first one's gone, and then the natural log secant of 0 was 1, tangent was 0, so we get a natural log of 1, which is also, again, just 0, which will just leave us with a 1/4 times that whole first piece. So we can put it as a root 5 over 2 plus 1/4 times log root 5 plus 2. All right, should have started further left, but everything's there. All right, and then for the surface areas, we've got a frustum here just to give you a picture, and they've got the surface area of a frustum of a right circular cone is S equals 2 pi r L, where L is the slant height and R is 1/2 R1 plus R2, or the average of the radii. We don't need to worry about that here. What we do want to take note of is L. L is what we were just doing above. It's arc length. Or the easier way to think about it here is that it's going to be a height. All right, so surface area we can think of up here instead of 2 pi r L, 2 pi r H. And all we're going to do is the same summative process we did for arc length, but we're going to do it for the surface area of all these little shells, you can think, right? So the 2 pi r H relates to the shells we did when we rotated for the volumes earlier. We had the thickness of each shell brought into play here. That's not going to happen here. Our H is just going to be our arc length formula. So we'll have the circumference times the height for each little disk to add up all these surface areas. So two different formulas we can use depending on our axis of revolution. If we do have a curve running this way that we're going to rotate around the x-axis, you can see the radius for that one is a y value, or what we usually call f of x. And so our surface area formula would be the 2 pi integral from a to b of f of x, right? That's our r, times our arc length. So the 1 plus f prime x quantity squared dx. So circumference times height, but we're adding up all of the ones as we slice all the way through to get our total surface area. And then if we've got a function that's going up and rotating around the y-axis. Right, we can see our radius there, r would just be some x value. So our radius is just x, and then for surface area, we'll have 2 pi integral, we can say from c to d for the y's they use sometimes, right? But of just x times that arc length, 1 plus f prime x quantity squared dx. And the arc length, again, is interchangeable. So if you were doing everything in terms of y, you would just have x equals f of y, right? We could put that in, and then 1 plus f prime of y dy. So it doesn't matter if we're doing x or y, we just want to make sure everything is written then with respect to x or y, whatever we're integrating with respect to. All right, so 2 examples. We want to find the area of the surface formed by revolving the graph of f of x equals x cubed on the interval 0 to 1 about the x-axis. So we don't have to have perfect pictures, but just to kind of see that radius the first few times, right? X cubed is coming up through here. We're only taking the piece from 0 to 1, say, and rotating around the x-axis means our radius in here is a y value, or f of x. So because we're still using arc length, we want to find f prime still, same as we did in the last section. F prime of x here, if f of x is x cubed, would be 3x squared. And then we'll sub everything into our formula for surface area. So we're integrating from, and here let's write the 2 pi out front. So 2 pi integral from 0 to 1, f of x, right, that's our radius, times our integral of 1 plus f prime x quantity squared dx. And then we can sub everything in. So 2 pi integral 0 to 1, f of x is x cubed on the outside here, times our square root of 1 plus our quantity 3x squared dx. Simplify algebraically, and then you'll see the work for these, I think, is sometimes easier than the arc lengths. We'll get a lot of nice little u-subs. So here we've got an x cubed outside, and when we square inside, we get a 9x to the 4th. So that x to the 4th inside, x cubed outside should make us think u sub. Our u, we can make the whole value underneath, 1 plus 9 x to the 4th. And then our du would just be a 36x cubed dx, or du over 36 would be our x cubed dx we can sub out, right? So that whole piece coming back. All right, which means we can write our surface area as a 2 pi over 36. Integral would go from now, ooh, I didn't do that. If I plug in 0 for x, I get 1 for u. If I plug in 1 for x, I get a 10 for u. Right, just using the substitution down there. And then I'd be left with just u to the 1/2 du. So we get a pi over 18 times the 2/3 that comes in from that antiderivative, u to the 3/2, evaluated from 1 to 10, which will give us a pi over 27 times 10 to the 3/2 minus 1. All right, and for that one, we've got an approximate value then of 3.563. All right, one more going the other direction. We want to find the area of the surface formed by revolving the graph of f of x equals x squared on the interval 0 to root 2 about the y-axis. So there's our parabola and the piece we need, 0 to root 2. If we're rotating around the y-axis, you can see that our radius here is an x value. Right, so our radius is just x. Our derivative, again, f prime of x is going to be 2x. And so for our surface area, we've got 2 pi integral from 0 to root 2 x times square root of 1 plus quantity 2x squared dx, which will give us a 2 pi integral 0 to root 2. X is still outside. Underneath, when we simplify, we get a 1 plus 4x squared. And so you can see that same relationship. We've got x outside, x squared inside. So we can make our u the 1 plus 4x squared. du then is an 8x dx, or du over 8 is x dx. And here, if we sub in 0 for x, right, if x is 0, u is going to be 1. If x is root 2, u would be root 2 squared is 2, 8 plus 1, 9. All right, so our surface area, our integral here becomes a 2 pi times the integral from 1 to 9 of just u to the 1/2 again, du. And we'll put that eighth out front. So we get a pi over 4 this time times the 2/3 again coming in from the antiderivative. And then we're evaluating u to the 3/2 from 1 to 9. So we get a pi over 6 on the outside. And then inside, easier this time, square root of 9, 3. Cubed is 27. 1 to any power is still 1, so 27 minus 1. All right, which would give us 26 pi over 6, or 13 pi over 3. An approximate, I wrote it down, so I'll give it to you too, 13.614. All right, so that's it. We'll practice both arc lengths and surface areas, and then I'll see you in 8.3 for the physics applications.